Hi, you are here, sitting in your coat. Suddenly, you see an apple falling. You say, wait, what? That's physics. So let's go back in time. No, not this back. Yeah, wait, what? Who's that sitting under the tree?
Ah, the legendary gravity guy. What did he do? Little Timmy asked. He found the threesome between force, mass, and acceleration, where mass was the curve.
Imagine force as a push or pull on something. It's like when you accidentally elbow your friend while reaching for the popcorn during a movie. Now think of mass, our pretty girl, as a block. It tells you how much stuff is crammed into an object, and yes, it's also the measure of inertia. A fat person doesn't like to change its motion. It's like when you're comfy on the couch and someone tries to drag you away. What do? You resist. The more the mass, the more your inertia, because a fat person cannot move very easily. Acceleration, our Pookie, is how fast velocity, which is speed, but with the direction, changes. Imagine you were riding a bike and suddenly you pedal harder. Happens, you speed up, and that's acceleration. Picture this: Newton chilling under an apple tree, minding his own business. Bam! An apple smacks him on the head. His reaction? That must have happened for a reason. And voila, he discovers gravity, the force that pulls masses together. Even you, my friend, attracts the universe. Though I know you can never attract a girl, but technically you do attract. Newton's like, let's put this on paper. So he does. The law says, hey, two masses, you're gonna pull on each other. How much? Well, it depends on your mass and how far apart you are. Bigger mass, bigger pull. More distance, smaller pull.
Planets in our solar system are like cosmic dancers. They got their initial velocity during the solar system's wild formation party. And guess what? There's no bouncer in space to kick them out. So they keep orbiting the sun forever. Newton's first law: once you start dancing, you don't stop until someone applies an opposite force. Picture this: you are paddling your cycle, so you're moving forward. But now you stop paddling. What will happen? Your cycle will eventually come to rest as friction force increases, which is in the backward direction, and voila, this is Newton's first law of motion. Cramped up on a space. Whether you're on Earth or the moon, it's the same. Your atoms can just decrease. But wait, that's a cosmic skills opinion. On Earth, it's like, hey, you weight X pounds. But on the moon, it's more chill. Weaker gravity, lighter weight. So technically, you are not overweight, but on the wrong planet. Okay, we are done with the Newton guy. Let's move to another part. Picture your phone falling from your hand. Grounds like surprise. Your phone broke. The culprit, energy. Energy's unit, the joule. But here's the twist. Energy is chill. No direction. Just digits, which is value. We call it scalar. While on the other hand, we have forces which are vector. They have both a direction and a value. There are two main kinds of energy: kinetic energy and potential energy. Kinetic energy is the energy of movement. If you move, you have kinetic energy. Potential energy, your phone held high, it's storing gravitational potential energy. It's like, hey gravity, I'm high up, please give me a reward. Gravity is like, okay son, take some energy, and that is gravitational potential energy. Work equals to force into distance. But wait, if you lift a weight and don't move it, no work happens. So lifting heavy stuff feels like work, but physics says nope, you are very lazy my boy, but trying to live that actually costs to energy. Energy is the ultimate party animal. It never goes, it just changes outfits. Conservation of energy, folks. Your phone screen cracks. Energy is like switching from potential energy to kinetic energy. When your phone is high above the ground, it has gravitational potential energy, but while it falls, the gravitational potential energy that is stored is converted to kinetic energy, as reducing height reduces the gravitational potential energy. But where does that reduced gravitational potential energy go? It just can disappear, and so it is converted to another form of energy known as kinetic energy, and that's the conservation of energy, my boy. The car that's moving has kinetic energy. When the car stops, assuming the car doesn't smash into a wall, where does that energy go? When you apply the brakes, there's friction between the brakes and the wheels, causing the car to slow down and creating heat as a byproduct. The heat is then dissipated to the surrounding air, and that makes the molecules in the air move faster, and things that move have kinetic energy. So ultimately the kinetic energy is transferred from the car to the air. With this knowledge, we can define that temperature is just the average kinetic energy of atoms in a system. You see, all atoms, not just molecules in the air, wiggle like this. The faster they move, the hotter things get. That is temperature. Now let's get to thermodynamics. It tells you when you jump in lava you will die, but most importantly it tells you about entropy. Imagine your room. When it's tidy, that's like an ice cube, everything neatly stacked. But when you toss stuff around it, it's like water, splish slash, no rules. Now zoom out to the universe. It's like a teenager's room after a wild party. Everything is tossed around and messed up, which is total entropy. And time, it's like a one-way ticket, no U-turn. So next time you spill your coffee, blame entropy. Entropy is basically the number of ways a molecule can arrange itself, and as time increases there are more ways in which a molecule can arrange itself, and thus entropy increases. And hey, about that gasoline, it starts all neat and orderly in your car's tank, but as it burns it goes wild. So substances with lower entropy, they're the responsible well-behaved guests who are the most useful at the time of need. Well, we had enough of entropy. Let's move on from this toxic relationship and try to find a new beautiful girl named electromagnetic. electromagnetism. Imagine there are two cousins who finally met at a family reunion. Electricity is like that hyperactive kid who can't sit still. Magnetism, on the other hand, is the cool uncle who knows how to attract attention. Picture two charged particles, one's positive and the other's negative. Opposite charges attract and like charges repel. It's a world without LGBTQ. A man goes for a woman and a woman goes for a man. They can't fall for the same gender. As electrons move, they create a magnetic field. Now bring in a magnet. It winks at the electrons and they attract each other. Imagine you're at a cosmic party and everyone's dancing, but some folks, let's call them electrons, get clingy. They stick to objects like your hair or that balloon you rubbed on your sweater. When you rub things together, one of the objects gets more electrons while the other loses electrons, and thus the overall charge of the two objects changes, and this is static electricity. Electricity which doesn't move. The electrons aren't moving. If we accelerate the charge, there will be a magnetic field around it. That magnetic field interacts with the electric field, which again changes the magnetic field, and this is a sort of chain reaction. Now this whole chain reaction creates an electromagnetic field that radiates outwards into space as an electromagnetic wave. Depending on the frequency, the human eye can actually see this. It's called light, but most of the spectrum is invisible to the human eye. Let's now dive into the world of particle physics. Particle physics studies tiny building blocks of the universe called particles. These little fellas are like the Lego pieces that make up everything around us. Imagine the universe as a giant Lego castle and particles are the bricks. Now let's meet our cast of characters, fermions. These are the introverts of the particle world. They include electrons, the shy ones, neutrinos, the elusive ones, and quarks, the colorful ones. Fermions follow the no two alike rule, which is they only fall in love with their opposite state. Bosons. These are the party animals. They carry forces and love to dance. They include photons, W and Z bosons, where W bosons carry out the beta decay, and gluons. Gluons hold quarks together inside protons and neutrons using the strong nuclear force. They are like the super glue of the particle world. Now we come to the four fundamental forces governing particle physics. Strong nuclear force. A strong force is like a clingy X. It binds protons and neutrons together in an atomic nuclei. It's super strong but only works at short distances. Imagine it saying, hey proton, are you made of quarks because you're attractive? Electromagnetic force. This force is an infinite range and is 1 by 100 as strong as the strong nuclear force. Particles with charge like electrons feels its electric bind. Weak nuclear force. The weak force is like a shy matchmaker. It's responsible for a radioactive decay and neutrino transformations. It whispers, hey neutrino, I have got a W boson who's into you. Wanna change flavor? Gravitational force, the ultimate wingman. It's weak but persistent. It tells massive objects, hey baby, let's attract each other forever. You complete my orbit. Antiparticles are like the evil twins of particles. They have opposite charges and spin. When a particle meets its antiparticle, it's like a cosmic dick. They destroy each other, leaving behind energy. Talk about a theory. Breakup. Okay, talking about breakup, let's break something up again, but this time inside an atom. I know you are thinking about radioactivity. At their center, there's a nucleus made up of positively charged protons and neutral neutrons. Most things around us are made up of stable atoms, but sometimes an atom has too many neutrons compared to protons. When this balance stable, it becomes an isotope. Unstable isotopes want stability, so they release energy and particles to regain balance. This process is called radioactive decay. During decay, they transform into new nuclei. Now picture a group of radioactive atoms at a party. Half-life is the time it takes for half of them to leave the dance floor. Some leave faster like gamma rays and some dance for years.
Wait a minute! Who are you?
So light is like the Usain Bolt of the universe, traveling at 300 million meters per second in a vacuum. That's faster than your grandma chasing the ice cream truck. Everyone's like, light's a wave bro. Imagine it as a chill surfer riding through two tiny slips. When those waves high five or fist bump, they create an interference pattern. Albert Einstein was like, hold my quantum coffee. He discovered the photoelectric effect and dropped the bomb. Light's not just a wave, it's a photon party. These tiny packets are like the universe's sugar. Anyway, he said, as he continued to casually drop an absolute bomb on the entire field of physics with his theory of relativity. He assumed the speed of light is constant because it arises from two other constants. He also assumed the laws of physics are the same from everyone, regardless if it's moving or at rest. Now think about it. If two people turn on a flashlight but one person is standing still while the other person is on a moving, wouldn't the person standing still see the other person's light being faster? But the reality is no. It would be the same as their own flashlight. That's impossible, except if time passes slower for that person from the perspective of this person. The speed of light is constant, time must be relative. Newton thought gravity was a force, but Einstein was like, nah fam, mass bends space-time. Einstein thought that the universe is a mesh of space and time, and anything with mass bends this fabric. Einstein dropped another bomb. Equals to mc squared. Energy and mass are best friends forever. According to this formula, even just tiny atoms can release a humongous amount of energy by giving up just a fraction of their mass during fission. What is fission? It's the same thing Oppenheimer used to make the bomb go. You see, there's two main ways to gain energy from changing nuclei: fission and fusion. Fission splits atoms like a breakup playlist. Neutrons crash the nucleus party and boom, energy release. Fusion is like a marriage of between two people producing a larger atom. So picture this, Einstein sipping his chai latte, scribbling equations, and bam, he accidentally stumbles upon a new whole universe, quantum mechanics. It's like discovering a secret TikTok dance challenge that defies logic. Then Max Planck, the OG German genius, slides into the DMs like Einstein's, you were onto something. He spills the tea. Life's not just a chill wave, it's a party of tiny packets called quantum energy. It's like a cosmic subscription box delivered in bite-sized portions. Electrons inside atoms, they're the ultimate multitaskers. They are here, there, and vibing everywhere. It's like they're at a Coachella, Burning Man, and a cozy Netflix binge all at once, and this is also quantum superposition. So Schrodinger, the OG quantum wizard, handed us an equation. Imagine it as a cosmic Tinder profile for electrons. Swipe right if you wanna find me. This equation gives a cloud of probabilities. The localize the wave, the more likely we'll spot the electron vibing there. Now let's talk about particle paparazzi. Imagine you are stalking a flying ball. In one peak you see its exact location, like a tag Instagram post. But in the other you are clueless about the direction and speed. It's the blurry UFO sighting. That's Heisenberg's uncertainty principle. You can't have both deeds at once. It's like trying to catch a sneeze and hiccup simultaneously. But wait fam, it gets weirder than a cat video gone viral. Remember the double slit experiment? Light beams are like party waves, high-fiving and chest bumping, but even if you send solo photons, they are like quantum influencers. They still create interference pattern. How? What did a single particle interfere with? Well, we think it interfered with itself because it acted as a wave and went through both slits at the same time. That's a superposition. Okay, well, let's just measure which slit it goes through. Yeah, that's not going to happen. Once you start measuring which slit the photon goes through, it stops acting like a wave and the interference pattern disappears as every particle chooses just one of the slits to go through. Sounds kinda suspicious to me, so hit that subscribe button.